Okay, so let us continue our discussion on second law of motion, or the equation of motion. So we're already familiar with some forces, such as the mutual force from law of gravitational attraction, the internal forces. Today we're gonna focus our attention to a special type of force, which is almost present as long as there is a surface, and these are frictional forces. So there are many types of frictional forces. There are kinetic friction force, static friction force, and rolling friction force. So these forces have a huge impact on any types of motion. So let's start with kinetic friction force. So this kind of friction force, it acts whenever there is a relative motion. So for instance, there is a box that is initially in motion. Either it is accelerating or not accelerating, as long as it is in motion, or it has a velocity and it is in contact with the ground or any surface, then there is a friction force that is present between or on the interface, and that friction is called kinetic friction force, which is notated as F sub k. In most cases, or in many cases, the magnitude of this friction force is experimentally found to be proportional to the normal force, approximately proportional to the magnitude of the normal force. So what is a normal force? A normal force is a force that is perpendicular or normal to the surface. So if we draw an FBD is isolating the object of interest and exposing all the forces that act on the body. So first we have the weight that acts on its center mass. We have the weight, that is the action force. So since our object is static, then there must be a reaction force that counteracts that weight. And we call this force as the normal force because it is perpendicular to the surface. So in a case that is inclined, the weight is still going downward, but the normal force this time is always perpendicular to the surface that is being considered. So experimentally, it was found that the friction force, the kinetic friction force, is proportional to the magnitude of the normal force, meaning that their relationship is simple, meaning it is just on average linear. If this is, for instance, this is Fk, this is normal, then the relationship is just linear. Of course, there are other unique phenomenon or special cases, maybe because of the types of material or extreme conditions, such as very low temperature. The characteristic of the surface is very completely different, especially at very low temperature. The surface physics is different, so we might have a relationship that is not linear. It may be like this, or it may be like that. But in most cases, meaning in everyday phenomenon and in most surfaces, the relationship between the friction force and the normal force are linear, meaning it is simple. So by converting this to equation, we must introduce a constant of proportionality. that constant is of proportionality is notated as mu sub k, and mu sub k is known as the constant of coefficient of kinetic friction. So the more slippery the surface, the smaller this coefficient. The smallest value of mu k is 0. It cannot be less than 0. Most values play within 0 and 1, but it can still have a value that is more than 1, because there's no rule that says mu k should not be more than 1. Alright, so still on friction force, remember that force is a vector, so Fk is a vector, normal force is a vector, and mu k is just a scalar. So this equation is not a vector equation. It is just a relationship of the magnitude of two vectors, which are friction force and the normal force. So going back to the phenomenon of this friction, this equation, although it looks simple, right? You might think that, wow, this simple equation can cover or completely and astonishingly describe the phenomenon of friction, but this equation is just an oversimplification of a complex phenomenon, because of course when you look at the microscopic level, there are irregularities on the surfaces, correct? So if we are going to magnify at that point, let's say, if we're going to magnify that point of contact, a particular point of contact, we may find a surprising surface, because really, no matter how smooth the surface is, it is always rough at microscopic level. So you may think that, well, maybe the source of friction is due to mechanical interlocking of these irregularities, surface irregularities, but that is not quite the case, because friction, especially both friction and normal force, not just friction, normal force and friction force are the results of the intermolecular forces. Intermolecular forces. So fundamentally, they are electrical in nature. Electrical in nature. So this is the real, or this is more of the origin of the friction force, not quite from mechanical point of view. But of course, mechanical interlocking might contribute to the effect of the magnitude of the friction, but it is well described using this principle or concept. So the intermolecular forces between the surfaces between the rough surfaces at points where they come into contact. So as the box slides, when you move, or as the box slides over the floor or over the surface, the bonds that are present on these points between the surfaces, they form and break, and therefore the total number of bonds varies, correct? So the kinetic friction force is not perfectly constant. This is not perfectly constant because the number of bands varies as you move or as the object slides past another surface. So when you increase the smoothness of a surface, what actually happens is that it doesn't decrease the coefficient of kinetic friction force. In fact, the opposite happens. When you increase the smoothness level, or when you reduce the roughness of a given surface, what actually happens is that it increases the value of mu k. It is because of the intermolecular forces. And there is a process in mechanical which is called cold weld that employs that principle, wherein one specimen is rotated at high speeds and rubbed against another specimen to the point that both increases their temperature so that they fuse together. Okay, so for another type of friction force, a friction force may also act even when there is no relative motion. So for instance, let's draw the same example. A box. Oh yes, what happened? A box sits on top of a given surface. So if you try to move a box, if you try to slide a box across this surface, this box may not move at all. It is because there is, of course, a force that counteracts the applied force. So for instance, you might push the box with a magnitude P, but upon doing it, the box doesn't move at all. So from the third law of motion, the third law of Newton, there must be an opposing force which equals your applied force. And this friction force is called a static friction force. This force is also found experimentally to be directly proportional with the normal force, just like with Fk. So by introducing a constant, we have now an equation for static friction force, and μs is called the coefficient of static friction force. So μs, the smallest value of μs is also the same with mu k, which is 0, and μs might also have a value that is greater than 1. So just like with Fk, the Fs, this equation is not a relationship between vector. It is not a vector relationship, but rather a relationship between magnitudes of two vectors. So to illustrate an example the relationship between the static friction force and the kinetic friction force and the transition from impending to motion, let's draw a series of boxes describing the status from state of rest to a state of motion. So first, we have a box, okay, wherein we draw the weight, we draw the normal force, and there was no applied force. The box is at rest, no friction, and of course Fs is 0 because there is no lateral force. It's just two vertical forces, the normal and the weight. On the other hand, if we try to apply a force, first we still have weight and the normal force, we apply, for instance, a force P on the right, but still the object or the box did not move or doesn't move. It is because there is an equal but opposite reaction force, which is the Fs. So the application of force is weak. The box remains at rest because the static friction force is less than μs n. Of course, the Fs balances the magnitude of P. But if you try to increase the magnitude of the P to the point that you max out the value of possible maximum value of Fs, then you are in a state of impending motion. So the Fs is now equal to its maximum value, which is μs n. So if you still try to increase the value of P, but Fs has already got its maximum value, then that's the time the box will start to move. So here you see that if you increase further the value of P, but Fs will only have a certain value, that is μs is equal to μs n, but this time P is greater than μs, and the body or the box will start to move. So from here we can draw a diagram describing that state of rest to state of motion. So this is the Fk, this is the Fs. Of course, the relationship between this is the force, the relationship between the friction forces and excuse me, friction forces and normal force are linear, both linear. So here we can see that when you try to increase the value of P, here you see that it is balanced by an equal amount of Fs. Let's just first erase this one so that you're not confused. Let's now just focus on Fs and P. So when you try to increase again the P, it is counteracted by static friction force. So here we see that in the case of first case, the scenario is there is no friction force. There is also no applied force. Okay. So let's do a bracket here. So this case pertains to this point. There is no applied force, zero applied force. So that Fs is also 0. But when you try to increase the value of P, but still less than to the maximum value of Fs, you might work within this area. It is still not enough to move the object, but of course the value of Fs adjusts to the value of P. But when you try to further increase the value of P such that you exceed the maximum value of Fs, then you are now at the impending motion. For instance, this is only the maximum value of Fs that can resist the value of P. So here we see that this is the maximum point at which the static friction force can still hold the object. And what is happening here is that the motion will start to move. And when the object is moving, the type of friction force that is present is not static anymore, because from here to here the state is at rest, but here the state is in motion. So if the object or the box slides, the type of friction that is present is now kinetic. It is not static anymore. Remember that. If the object is at rest, static only is present, but if the object is in motion, kinetic is only present. There is no way that both friction forces occur at the same time. So here we have this. But since mu s is greater than mu k, the resistance offered by kinetic friction force is always less than the maximum value of the static friction force. So what happens is that the resistance drops a little. And of course, it is not a straight line because, again, as we have discussed, the value of the number of bonds present between the surfaces varies. Therefore, the magnitude of the kinetic friction force also varies. So this can also be, that's why it can also be a value of Fk, which is this height. That is the value of Fk. So this is in at rest, while this is in motion. Okay. So any type of material paired with any other type of material, they create different values for mu s and mu k. So this is a table for approximate coefficients of friction between different materials, coefficient of static friction, coefficient of kinetic friction are both displayed. So we can see that a value, most of them are around 0.4, 0.3, but of course there are coefficients that are greater than 1. Example is rubber on concrete, dry, and copper on cast iron. They are greater than 1.